Hello everyone and welcome to the official YouTube channel for Wayne State University's chapter of the Tau Beta Pi Engineering Honor Society. My name is Austin Heitzman. I'm back again with another installment of our Linear Algebra tutorial series, and today we will be finishing up chapter 2 by looking at linear independence. This is chapter 2, section 3. We have to warn you ahead of time, at least for me, this content really felt sort of like a brick wall until I just started attacking it from every possible angle that I could think of. So some of the definitions and initial overviews might seem a little impossible, but I am going to try to make this as understandable and digestible as I can, and hopefully by the end of it, your idea of independence will kind of clear up. So we're going to start with the standard, straight from the textbook definitions, and then from there we can kind of look at it from a more intuitive angle. So we can say that a set of vectors is independent if it satisfies the following. So say we have a set of vectors called S, right? And that includes just as many vectors as it goes up until, say, the letter M, right? If that set of vectors is in that Euclidean n space, like we talked about recently, then the set is independent if and only if the only solution to this linear combination, so like C1v1 plus C2v2 plus all the way up to CMVM equals 0, which we talked about in the last video with linear combinations. So if you're rusty on that, please check that out. If the only solution to this is the trivial solution, which is all of these scalars, C1, C2, all the way to Cm, equal each other, which all equal 0, right? So if the only way that you can get this system to equal 0 is setting every single scalar to 0, then the system is linearly independent, right? Conversely, if this is not true, right, if the above linear combination has a non-trivial solution, then the set S is linearly dependent, right? Now, what in the world does that mean, right? Personally, when I first started this chapter, it took me a very long time to wrap my head around why that was important, and what finally did it for me was looking at the geometric interpretation. So let's try to sketch these out. Say that I have two vectors, right? We can call it v1, v2 are vectors. So let's start with the independent, right? Now we know that for a vector to be in standard form, it's gotta start at 0, right? We're gonna start up at the origin. And for our purposes, I don't care what these vectors actually equal, right? I'm gonna say that this guy is v1. I'm gonna put v2 somewhere over here. Now this system is gonna be independent. The set of vectors v1 and v2, these are independent. And you're going to understand why as soon as I show you what the dependent vectors mean. So in a dependent space, I'm going to start at 0. I'm going to say that v1 is this guy. I'm going to say v2 is this guy, right? These overlap. My drawing doesn't exactly show it, but these are on the same line, right? So what did we just say in this definition, right? We are breaking these vectors up from the set S into a set of linear combinations, right? Which is essentially adding them up and taking each component multiplied by a scalar, right? That's those C1, C2s, so on. So linear independence means that if the only way we can get this to equal 0 is by setting all of these scalars to 0, then they're independent, right? Well, in the independent graph, we have exactly one spot where both v1 and v2 equal 0, right? So if we sketch out this little C1v1 plus C2v2 equals 0, well, the scalars that we're multiplying, C1 equals C2 equals 0. That's true, right? There is no other scalar along these two vectors where we can place both of them at the same time. They don't intersect anywhere else, right? Whereas these guys, well, they do, right? I mean, vector 1 and vector 2 are equal to each other from tip to tail of vector 1, which means that we can get those scalars to equal something not 0 and still have this combination equal each other, right? So in that way, I mean, it becomes clear like what dependence means, right? Because now we can say that vector 1 is clearly dependent on vector 2, right? Because it's literally contained within it, right? Whereas these guys, I mean, vector 1 can exist, and if you take vector 2 out of the picture, it doesn't even notice. The only spot they touch is at the origin. So hopefully that clears it up a little bit. And again, this really just a matter of like trying to tackle this from as many different angles as you can. So another part of it too is just like doing a bunch of problems. So let's look at how to solve these things. There are two different scenarios that we're going to focus on here, and one of them is for vectors, which are basically, as we know, like matrices with only one column, and the other way to do it is going to be with matrices themselves. So when we start getting into the 2x2s and everything. Let's start with vectors. So say we have just like vectors v1, v2, and v3 vectors. The way that we want to lay this out, well, remember that we're basically testing if a combination of these can equal 0 with each scalar multiple equaling 0, and that's the only solution. If we want these to be independent, that's how it's going to have to be. So the way that we can lay this out is basically setting that up, right? Usually when you're given a problem, you're not given like the standard V, right? If you remember in last video when we talked about linear combinations, in order to figure out if a set of vectors were a combination of some solution, we were given the solution. In this case, though, I mean, we know that C1, V1 plus C2, V2 plus C3, V3. This is what we're trying to figure out, and we want it to see if it will equal 0, right? So we're going to basically set V to equal to 0 vector, right? And basically the first step is just going to be putting it in that form. And then from there, we can convert this to a system and solve. And what does that mean? Well, honestly, even in a textbook, it says like you can do this by like an actual linear system. So option 1 would be like actually getting a system of like a system of equations like we've dealt with before. All of which are going to equal 0, right? Or perfectly acceptable as well is to just put this in, it can be an augmented matrix with the 0 vector as the solution. But honestly, no matter what we do to manipulate this, and of course when I say solve, I mean get into row echelon. No matter what we do to get this into row echelon, this column is always going to be 0. So you really don't even need to have this as an augmented matrix. You can just have it as a matrix. Yeah, so basically the idea is exactly what we've been doing from the start. put it into some sort of system of equations, whether it be a linear system or just a straight up matrix, and bring to row echelon form, and see what comes out, and we will analyze those solutions in just a minute. But first I want to just briefly touch on how to do that with matrices. It's basically going to focus on mainly 2x2 matrices, but the concept is going to be the same for any size. So matrices can be a little bit trickier than vectors, right? Because you're going to be given like a set of like 3 or 4 matrices and asked whether they're independent, right? Well, the question is, with vectors, since vectors are just one column, we can very easily put this into a matrix where column 1 is vector 1 and column 2 is vector 2 and column 3 is vector 3 and so on. How do you do that with a matrix, right? It can get a little complicated at first, but once you start doing it and once you kind of see the pattern, it does kind of click. But the idea is pretty much the same, right? So if M1, M2, and M3, we're just going to say 2x2 matrices. The idea, C1M1 plus C2M2 plus C3M3 is 0, is what we're looking for, right? So if they're dependent, then C1 equals C2 equals C3 equals 0, right? Now, to get this matrix, to get all of these matrices into one matrix, you basically need to add up the individual cells and then transform that into a linear system before you can transform that into the augmented matrix. What the heck did I just say? It's going to be pretty much impossible to properly explain this without at least some sort of example. So off to the side here, I'm just going to define M1. We're just going to say I'm just pulling numbers out of thin air just for an example here. All right, so basically we want to take these 3 matrices and form a linear system out of them, right? So that we can analyze these scalar multiples. So in order to do that, well, I know the result is going to be a matrix, right? Because that's what we're after. And the contents of this new matrix is basically going to be a combination of this, right? Now I know that if we are putting this into this system right here, right? Maybe it'll be a little more helpful to rewrite this over here. Well, now I know that everything in matrix 1 is being multiplied by this first scalar multiple, C1, and everything in matrix 2 is being multiplied by the second scalar multiple, C2, and everything in this third matrix is being multiplied by this third scalar multiple, C3, right? So we can use that. We can basically take C1, C2, and C3, just like we did last time in the linear combinations video. We can use those as our variables and then build our system using that. So in order to get this into a matrix, what I can say is I can basically start with this very first cell, this 1, 1 cell, right? Well, I see that for M1, we have C1 times 1, which is going to be, let's do this color-coded so you can see very clearly, 1 times C1 plus we have 2 times C2 plus we have 1 times C3. All right, that's going to be our first cell. And then this second right here, I'm actually going to erase that bracket for now so that I have room. The second one, we can do the same exact thing, right? So I'm getting 0 from this, and then C1 plus 3C2 plus another 0 C3, right? And for the first column, second row, I'm going to get 2C1 plus 5C2 plus 0 C3. And same exact thing for the last one. 2C1 plus 7C2, excuse me, plus 1C3, right? And then, of course, you can simplify this. C1 plus 2C2 plus C3 is our first cell. The first row, second column is just going to be 3C2. The first column, second row, 2C1, I don't know why I keep writing I there, TC1 plus 5C2, and then that last position, 2C1 plus 7C2 plus C3, right? All right, so now that we've broken this up into its own matrix, well, we can basically use this right here, and write this into a linear system, right? Because this is pretty much equivalent as saying C1 plus 2C2 plus C3. Second equation is 3C2. Third is 2C1 plus 5C2. Fourth is 2C1 plus 7C2 plus C3. And remember, we want all of this to equal 0, right? So when I write the solution, each of them is going to equal 0, right? And from there, you can put that into an augmented matrix by just grabbing the coefficients, right? So that is the long way to do it, as you can tell. And it is a good way to get into the habit of knowing what goes where, right? However, there is a much faster way so long as you don't get things tripped up, all right? I'm going to show you just like a really sneak preview of that. So in order to do that, let's write this coefficient matrix. So that would be a 1, 2, 1, 0, 3, 0, 2, 5, 0, 2, 7, 1, right? Hopefully that's clear where I got all of that. Now, if we look at this in reference to our original matrix, right? Maybe I can zoom out a little bit so we can see these on the same screen. So I'm looking at this, and I'm looking at this, right? Well, matrix 1 has essentially turned into column 1, right? Because we have 1, 0, 2, 2, right? And matrix 2, 2, 3, 5, 7. And did it hold up? Yeah, 1, 0, 0. Whoa. One. So basically, like the matrices kind of unfolded themselves into vectors because of this long process, right? And if you can really solidly remember which cell goes where in this vector, then you can easily jump from here to here without having to do any of that in between. However, it's very easy to mess this up. You know, what if you start thinking it actually goes like 1, 2, 0, 2, then that's going to give you a completely different answer. So I show this to you so that you know it's there. However, be cautious and use it at your own risk. All right. So that was a long sidebar, but I guess it's important to understand how you can actually go from like a set of matrices to a vector. So basically I'm gonna see sidebar to answer this question, right? And once you've gotten to that point, I mean, this is going to be the exact same thing as we just talked about vectors, right? The next step is basically get into a system and solve. See what comes of it. See if we can actually make all of those constants, the scalar multiples equal 0, and see if that's the only thing we can do, right? Now, to interpret these results, I know I keep saying, like, they all need to equal 0. Well, what does that really mean? Well, basically, I mean, say that I'm just going to put this as like a 3 by 3, right? And I'm just going to draw it out as if it's already in reduced row echelon form. Right? Well, from here, I can tell that C3 must equal 0, and C2 must equal 0, and C1 must equal 0, right? So something like this will give an independent result. We'll put that in quotation marks because I don't know if independent result is really the best term, but I think you understand what I'm saying. On the other hand, if we have like a C1 and a C2 and a like a nothing down here, something like that. Apologize, actually I'm going to change this just a little bit. We're going to say that C2 and C3 are in this column, and then the last row is just nothing, right? Well, in order to define C2, we need to do that in terms of C3, right? We would need to subtract C3 from both sides, and then of course at that point it wouldn't be 0 at that point. So something like that will give dependence, because C2 would again depend on what C3 is. And you'll notice too, like, just as a little preview, this column does not have a pivot. And that's going to be a really important indicator as we start analyzing everything. So hopefully this gives you an idea of what we're working with. Thankfully, because that is a lot of work, there are a few sort of shortcuts that we can keep in mind. And I say shortcuts loosely because they don't like always get you around it, but there are a few things that you can kind of test for at first, and you know, if they meet these criteria, then you can pretty much stop because you've proven that they're dependent, right? Okay, so for the first one, we're going to say that S is a set of vectors v1, v2, all the way down to vn in R sub m, right? So the general rule is if n is greater than m, then S is dependent, right? So basically, if the number of vectors is greater than the Euclidean space dimension, then immediately you can term it as dependent. And basically what that means is that when you reduce this, there's going to be at least one free variable, you know, like there's not going to be that clean, you know, that 1-to-1 ratio. You're going to have something like this, right? So that's the first shortcut. The second is a little bit easier to wrap your head around. Basically, if S contains the 0 vector, the set is dependent. Which again makes sense, right? Because at that point, 0 would be a column like this where there's no pivot. And the third one, let's word this like if one vector in S is a scalar multiple of another. So like, for example, like if v1 is equal to some constant times v2, then the set is dependent. So there's going to be one more that's a little less straightforwardly like check and see. It's going to come in 2 parts, and they're pretty much equivalent. So if S is independent, then any subset of S is also independent. Which makes perfect sense, right? I mean, if you have like a set of things that belong with each other, and you take a little chunk of that out of it, well, that's still going to belong with each other in the same way, right? Like, it just wouldn't make sense otherwise. And similarly, if, let's say T is a subset of S, and T is dependent, S must also be. Which basically says, like, if there are just 2 vectors that are dependent on each other in a set of infinite vectors, it doesn't matter how many there are. If there are at least 2, then the entire set is going to be dependent, right? So basically what have we learned from this is if there's any column lacking a pivot, then the set is dependent. That is basically what all of this boils down to, right? And the rest of it is just little shortcut ways to visualize that quicker. So we are almost done, I promise you. There's just a couple other things that we need to cover. The first thing I just really want to quickly touch on regards to determinants, something that we covered in chapter 1. If you need a refresher, I highly recommend you go check out that video as well. So I'm not going to go into the definition of determinants. Like I said, there's a whole other video to do that. But just as a quick reminder, we know that determinants can tell us two. The first is that, let's say that we're talking about like a matrix A. Right? So a non-zero determinant of A will tell us that A is invertible, right? And that AX equals B, that matrix equation, has a unique solution. Now, interestingly, now that we're learning about independence, a non-zero determinant also is a cue that the system is linearly independent. And this turns out to be like an if and only if, like if the determinant does not equal 0, then it is certainly linearly independent, and if the determinant does equal 0, then it is dependent, no holds barred, right? So if you have like a quick 2x2 sort of thing where it's really easy to calculate the determinant, that can be a very quick way of getting around all of this, right? And the last thing I want to mention, I promise this is the last thing before an example, is just some statements that we can now recognize as being entirely equal to each other, right? So say we have a matrix A. This is a square matrix, so like an n by n, right? Well, that means that if any of these statements are true, then all of them must be true, right? So saying that A is invertible is the exact same thing as saying that its matrix equation has a unique solution, which is the exact same thing as saying that its homogeneous system has only the trivial solution, which is the exact same thing to saying that it is row equivalent to I, the identity matrix, which is the exact same thing as saying that its determinant is non-zero, which is the exact same thing as saying that its column vectors are independent, right? So now, through chapter 1 and now what we have with chapter 2, we've managed to string together all of these crazy concepts that just seem so far removed from each other, but now we see they're actually saying pretty much the exact same thing, right? Like if one of these qualifies, then immediately we can tell all of these other things about it, which is honestly kind of a hidden gem of this subject so far, so just a nice little tidbit that I wanted to mention, and I'm sure as we go on with the course we're going to see a lot more of these little hidden threads pulling everything together. So I'd like to thank you for staying with me as long as you have. I wanted to do just one example so that we feel really grounded and secure, and only so long as you understand that true grounding and security in the subject is going to come with you doing a lot of these problems on your own. So let me just try to get you started with this one right here. Our task is to determine whether these matrices are linearly independent. Right. Now I just spent a lot of time earlier going through the long way of figuring out how to set a problem like this up, right? We had basically all of these coming together in one scalar multiple, and then the second one's coming together with another, and the third's with another, and the fourth's with another. You can go ahead and rewind if you want to see all of that again, but I am just going to jump straight to the shortcut way, right? Basically, I can see that matrix 1 is going to form a column vector like so. Matrix 2 is going to be the second column, and matrix 3 the third. And we can append that as an augmented matrix, which is the 0 vector on the side, right? Now, in order to solve this, we need to, say it with me, row reduce, right? So in order to do that, I'm just going to start with swapping the first and last rows, because I would much rather pivot with a 1 than with a 3. And I'm honestly not even going to write that last right here, because again, no matter what we do to this matrix, the coefficient matrix, that solution vector is not going to change because it's all 0, right? Okay, so now that I have swapped out those rows, we're just going to work on eliminating these. I'm just going to go through this a little bit quickly because we have done it so many times now. But if you need a refresher, we have plenty of videos from chapter 1 going into how to do this. From here, all right, that's going to give us 0 there, 1, and it would be at 6 minus 1 would be 5, 0, 0, minus 1 is 3, 0, 0, 7, it looks like in the last one. All right. Now, the neat part about all this is we don't really need to put this all the way into reduced row echelon form, right? And the reason for that is because I can look at this and I can see that, like, we could keep reducing and get this last row to equal 0. We can keep going as long as we want, but at the end of the day, you know, I can already see that each column has a pivot, right? Which means that, you know, if you really want to take this all the way out, let's say that this is C1, this is C2, and this is C3. Well, in that case, remember, we just have zeros on this side, right? So that means that 7C3 equals 0, so C3 equals 0, right? And putting a 3 there instead of a 7 doesn't change that, so that's fine, right? We already established that that's 0, so this is going to equal 0, and then you have C2 equals 0 and C1 equals 0. We can tell that C1 equals C2 equals C3, which equals 0. Therefore, this is linearly independent. All right. That was a lot, my friends. Thank you for joining me in this process. I hope that this does clear some things up for you. Again, it is just going to take a lot of practice. I highly recommend even just like going online and trying to think of like other approaches to view this problem of independence versus dependence. This is going to be something that comes up a lot through this course. It's kind of an integral part of linear algebra, so your future self will thank you if you just study it right now. Yeah, and we will have plenty more videos to come on this subject and many more on our channel, so please don't forget to like and subscribe. You can find pretty much any source of video on any engineering topic you can think of on our channel, and I do plan on doing plenty more of these linear algebra videos in the future, so stick with me, folks. In the meantime, happy studying, and I hope you have a great day. Bye.